Okay, thank you very much. So today I want to talk about low-scale inflation. In particular, I will show a relatively generic prediction of low-scale inflation. So this talk is mainly based on the paper. I want to with this archive number. It is in collaboration with Haruto and Yuma, who are my student. Haruto is the first year of master course. Yuma is the third year of the PhD. So before going into detail, let me slightly introduce my group at Tokyo Metropolitan University. So this is the Japan's map, and so Tokyo is here, and we are here. Although our name is Tokyo Metropolitan, but it's around the boundary of the Tokyo. But this is uh, not so bad place. If it is sunny, so sometimes you can find Mount Fuji by eye, which is close to the this place, but not very close. But this Mount Fuji is kind of one of the uh, symbol of Japan, so you can see it. There is also a famous mountain called Mount Takao, which is famous for hiking. So this is I remember this maybe 30 to 1 hour of train. You can reach here, and if you climb up to the mountain, you will find an interesting temple for Tengu, which is a legendary devil in Japan. It's a little bit scary, but if you go to the other direction, just two stations away, just maybe 10 minutes or something from our university, you can find the Sanrio Puroland. There is a cute Hello Kitty, maybe this angel. So therefore, we are in between the angel and devil. So if you're interested in our group or the environment or discussing physics, feel free to visit us. Basically, we have a digital program. If you, yeah, for collaborations, and we can basically uh, uh, support your local expense. Okay, the plan of today's talk uh, consists of four parts. The main part is the third part. So let me first briefly introduce inflation. So basically, the inflation is the exponential expansion of the, in the modern cosmology. It characterizes the beginning of the universe here. So this is the focus of today's talk. In the language of the energy density of the universe, by varying the scale factor over time, during the inflation, the energy density is almost constant. According to the Friedman equation, one can easily find that the space expands exponentially in time, cosmic time. I mean, later we have a reheating phase, which in which the energy is of the universe dominated by the infraton, and then we shift to the Big Bang cosmology with the hot uh, uh, universe. This kind of early history of the universe can be characterized by particle physics by introducing a scalar field called inflaton. This scalar field is supposed to have a potential with almost flat direction. So this scalar field can slowly load towards the potential minimum. Uh, because this is so flat, then the energy density changes slowly. Therefore, we can have an almost constant energy density, and we can have the inflation. Later, it starts to oscillate around potential minimum. Then we have the reheating phase. By copying this inflaton to some of the particles, then somehow this inflaton can decay into the some particles. Then we can make up the hot universe. The energy is transferred into the radiation. The important thing is that this is the quantum field theory. Therefore, this inflaton acquires some quantum fluctuations. Uh, uh, Yeah, this quantum fluctuation, becomes, the variance of the infraton field here and there. Then, the expansion history is slightly perturbed. Therefore, we can obtain the density perturbation through the decay of the infraton through the reheating. Uh, this kind of the quantum fluctuation becomes the density perturbation. This density perturbation is a seed of the structure of the present universe. We can have a galaxy thanks to the this kind of initial fluctuation. So therefore, our galaxy itself is an evidence of the inflation uh, theory. Another very important evidence of inflation is the cosmic microwave background anisotropy. From the data, one can obtain, from the anisotropy power spectra, one can actually reconstruct the initial curvature perturbation generated due to the quantum fluctuation of the infraton. One can see this is almost scale invariant. This is nothing but a prediction of the inflation. And this is the slight tilt. This is nothing but the prediction of the slow low inflation. From those data, one can actually get some information among the derivatives and the height of the inflaton potential when the inflation takes place. So we have some conditions for the inflaton potential. For instance, we to get the amplitude of the curvature perturbation, we can get this kind of condition between the inflation potential and the fast slow low parameter defined like this, epsilon. And we can also get the relation with the second slow low parameter by considering the slope of this kind of this power spectrum. So it's surprising that the one can already get the various informations of the inflation model, and this is the model for the beginning of the universe. Who can believe this? For maybe people in 100 years ago, but yeah, it is. So, but still, we don't know the whole uh, picture of the inflation model. For instance, we don't know what is the absolute value of the inflation scale. If we can detect some tensor mode, which is due to the primordial gravitational wave, actually we can get the scale of the inflation. But nowadays we cannot. We still did uh, uh, did not detect the tensor mode. Therefore, we get the upper limit on the inflation scale, which is around 10 to 12, sorry, 16 GB. So as a model builder, we have two ways to go. One is to consider the inflation models with potential energy around 10 to 16 GB. In this case, we can, in the future, we can, test this kind of model via LightBird or Simon's array telescope. Uh, Observatory. On the other hand, we can also consider the possibility that the inflation scale is much lower than the 10 to 16 GB. But of course, this inflation model should be much higher than the or higher than the MEV scale, because otherwise the temperature of the universe at the Big Bang after the Big Bang cannot be higher than the relevant temperature for having the Big Bang nucleosynthesis. Uh, yeah, today I want to focus on the latter possibility. The reason I want to focus it because we have various advantages when we consider low-scale inflation. I will not discuss in too detail, but I would say that when if the inflation scale is low enough, then in uh, various dangerous uh, uh, degrees of freedom in uh, very motivated UV compressions of the sun models can be just settled into the vacuum during the inflation. Therefore, we can have safe cosmology. Also, sometimes we can even consider the minimal kind of setup that infraton itself is the decaying dark matter. The long lifetime of dark matter is guaranteed by the small scale of the inflation and the condition for having the slow low. Sometimes we can also relax the cosmological constant during the inflation when the inflation scale is low enough. Uh, or we can more simply just say that uh, so the low scale inflation is more conservative because actually we don't know if the quantum field theory or framework for physics is valid with the energy scale much higher than the scale for the collider that we have that's what we have just proved. On the other hand, we also have some disadvantages. It is usually said that if the inflation scale is so low, then we have fine tuning. We have two kinds of fine tuning. One is the fine tuning for having the slow low to have a flat enough potential. Another fine tuning is initial condition. So we need to put the infrared field in the position that the potential is flat. But those kind of fine tuning can be actually at least partially addressed by model building. And sometimes, well, in most of times, the inflation will predict some eternal inflation. So in eternal inflation, we have, infinity, at least the volume will inflate infinity. So then we cannot actually simply compare the models by some number because we have a basically major problem. So we need to define measure to deal with fine tuning. Therefore, today I will not go into too detail about fine tuning and just assume that the inflation happens. Uh, well, the next disadvantage is the model dependence. So in the high scale inflation, we have a model independent prediction. That's the primordial, the gravitational wave. But for low scale inflation, what is the model independent prediction? This is a issue that I will tackle today. So I will show that there is a model independent prediction that is a shockwave formation soon after the inflation. To show this, I want to briefly introduce the formalism that we consider. Uh, let's suppose that the inflation potential is kind of analytic. Let's suppose that we can expand the potential around the field value that the inflation takes place. I take this potential value to be zero without loss of generality by the field redefinition. Then we usually have a genetic data series. Uh, However, I would say that I can start with the series from the 2n, which is the power of the inflaton, and I will neglect the lower dimensional term. Uh, uh, this is just for inflation to happen. This is just the fine tuning that I have just mentioned. And then we have also some even higher order dimensional term. Yeah, I assume this term it dominates the at least a few EFOs, last few EFOs for inflation for the slow low. Here I consider this coupling or coefficient of this term is negative so that it goes down rather than going in the positive direction for phi. Here we consider two kind of cases. N is half integer or integer. When n is half integer, the potential shape is like this. Uh, when n is integer, then we have the hilltop inflation. This case it is called inflection point inflation. One can also consider this n is one half of one, but it is known that the inflation is not successful. Therefore, I will not consider this case. We only consider this is cubic or more order of phi. So before going into detail of the inflation dynamics, let me briefly uh, mention that the vacuum structure, of course, this depends on some assumption, but just for simplicity of the discussion of today's talk, I consider the higher dimensional term just stabilize the potential. Namely, it gives thanks to this phi to n plus one term, or even higher, then we can have the vacuum. This vacuum means the vacuum energy is zero. Therefore, due to this the leading term, the scalar field is settled to the minimum, and then the field excursion can be just calculated by equating the v zero, the height of the potential around the phi equals zero to be lambda phi to n. Then we get the field excursion or BEP of the phi roughly given in this form v0 divided by lambda to the 1 to divided by 2n power. Then we can also get the typical scale of the curvature or typical mass of the inflaton. This is just the potential height divided by the field excursion given like this. So I should also mention that this V is usually much smaller compared to the Planck scale because this is low scale inflation. In the past, it is called small field inflation. So the field excursion is super small, and we get the mass much higher than the Hubble, which is V0 divided by n Planck. Okay, now we are ready to discuss a few about the genetic implication of low-scale inflation. So from the scalar amplitude, one can actually get the ratio of the V, the potential during inflation and the fast solo parameter. So immediately we can find when this V is small, the epsilon, the fast solo parameter, is also small. Therefore, usually this epsilon is negligible during the inflation for low scale. Then immediately we can find that the V-inf can be safely approximated by the V0. So the change of the potential can be just neglected during the inflation. The dynamics is mostly driven by the second slope parameter eta, especially the end of the inflation is characterized by the violation of the slow low condition by using the second slope parameter like this. So immediately we can derive that this condition is nothing but the uh, the uh, the the period when the curvature becomes as large as the Hubble scale. So, as I mentioned, this curvature scale, the Hubble scale, is much smaller compared to the typical mass scale of the inflaton potential. Therefore, what I'm trying to say is that the negative curvature suddenly changes from minus h inf squared to minus m phi squared soon after inflation. So it decreases a lot. Okay. So this is kind of an important feature for the low scale inflation. And I believe this is a genetic feature for once we have a low scale inflation for analytic potential. Okay, now we are ready to talk about tachyonic shock, which is the phenomenon that we found. So what is tachyonic shock? So this is the phenomenon soon after the inflation, and we focus on this short period after the inflation end. Then this is a kind of numerical, the result for the numerical simulation, and the animation shows that we have a shock wave expanding and collide with each other. So what is happening? To explain the dynamics, I separate this short period into three stages. The first stage is called explosive tachyonic instability. To understand this stage, one can follow some nice papers in the 20 years, maybe 30 years, 20 years ago, 25 years ago. Uh, so we just expand the equation motion by using the expanding the scalar field, the infraton field, uh, 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 with the homogeneous part and the fluctuation. So of course, the homogeneous part is the average of the infraton field in the volume that we are considering, and this fluctuation is the kind of variance from the average. Yeah, here because I will consider the small scale dynamics. So I how to say and I will consider the uh, very short period. So I just neglect the expansion of the universe. So we get the evolution of the homogeneous part like this, and we get the fluctuation at the linear order uh, evolving following this equation. So one can easily see that when the momentum of this fluctuation, the Fourier mode, is neglected, then because of negative mass, the mode we have the uh, growing solution uh, due to this term. Okay. So in other words, because we have the potential, changing, uh, I mean the curvature changing very fast. Therefore, if we consider some fluctuation in the space, so as when this quantum fluctuation gives a slightly larger field value, then this field value will load faster compared to the field value that smaller, right? So then we get this fluctuation growth. So this is the dynamics of tachyonic instability. By solving this equation in our setup with the power law terms, then we can immediately find that the mode with the initial condition uh, of the effective mass growing mostly. Uh, so in our case, because we consider the end of the inflation, the initial condition is nothing but the Hubble because this is the condition for the end of the inflation, right? So therefore, the mode of the Hubble grows mostly, and in total, or the by in the the space, not the Fourier space, but just the real space, one can see that the mode growing like this. So it's following the power, of n to the this phi bar. And this phi bar inf is the field value at the end of the inflation. So basically, uh, if we increase this phi bar a lot, then we can get sizable delta phi. And if we divide by this phi bar, then one can see that this phi bar, I mean this ratio grows with a positive power of phi bar when the inflation is successful. Namely, when we consider n is larger than unity. Okay, so yeah, in fact, this ratio, uh, how to say, uh, but anyway, so we can check if how much this fluctuation can grow. This ratio can grow by taking into account of the CMB data for the inflation potential. Then we get this kind of plot. The horizontal axis is the scale of the inflation. The vertical axis is the fluctuation when the phi bar is around the BEP. divided by the BEP. Namely, this is the typical scale when the higher dimensional term becomes more important. So until this time, until this value, one can at least in our discussion for this talk, the dynamics is mostly controlled by the leading term that I had just mentioned, phi to n term. Okay, so when the n is 3 over 2, one can see that this ratio becomes unity when it is around 10 to 5 GB, and this is larger than unity when it is smaller than 10 to 5 GB. So this means that when the scale is lighter than the 10 to 5 GB for n equals 3 over 2, we reach to the their phi around the phi bar before it lows down to the minimum. Okay, so this means that before it go down to the vacuum, we already enter into the nonlinear region because our calculation is only valid when this delta phi is much smaller than phi bar. But now it is unity, then we cannot trust our previous calculation. We need to take into account more serious calculation. Okay. On the other hand, when we consider it is hilltop inflation or n equal 2, then the condition is relaxed. This is 10 to 9 GB. Or if we consider much larger n, then we can even more relax it. So what is happening is like that. So if we consider low scale inflation, if we consider inflation scales, the lower the inflation scale, then we need to change the potential very fast to from the slow low to the end of inflation. This implies that the potential change a lot. Then this implies that the just the front of the fluctuation drops down, so we can enhance the fluctuation a lot. Then we can get the we can easily reach to the nonlinearity. And this kind of nonlinearity is must reached when we consider the inflation scale lower than the 10 to 5 GB for the inflection point and 10 to 9 GB for the hilltop inflation. And sometimes we can reach it when the inflation scale is lower than the 10 to 12 GB, but we can never reach it for the single oscillation. During the single oscillation when it is much higher than the 10 to 12 GB. Today, I will focus on those regions. I will not consider so high in scale inflation. So the inflation scale must be lower than 10 to 12 GB for today's talk. Okay. Now, once this fluctuation reach to the nonlinear regime, we need we enter into the second stage. To study the second stage, because this is nonlinear, we need to be more serious. We use lattice simulation to check what is happening, and this is a result by considering this kind of potential. We also consider other potential, but I will not discuss for this talk. Please check our paper. So the horizontal axis is the cosmic time, but just the time of simulation. Sorry, I didn't consider expansion here. But anyway, so just the time. The vertical axis is a normalized field value. So for instance, this black solid line denotes the average, the field value or homogeneous mode normalized by the buoy. And the black dashed line denotes the fluctuation. One can see indeed this fluctuation catch up with the phi bar, and suddenly it increase. It's broad. It bring the average field value to much larger field value. If we take the fluctuation less by hand, then this will slow low until much larger time, then it start to oscillate around minimum. So this is totally different dynamics from the usual oscillation behavior. So what is happening during this nonlinear regime can be found from this snapshot corresponding to this period. So one can see that this is snapshot for gradient energy, and the brighter place we have a larger gradient. So one can see that the gradient is somehow stored around the surface of this kind of circle. This is 2D simulation, so this in the 3D case this should be a bubble, and we have the bubble expansion. Or we could say this is a shockwave expansion, and then they collide with each other. So what is happening? So once we have the no in the nonlinear region, we can say that the fluctuation in the real space can be order one compared to 5R. So at some point, we can have an order one larger field value compared to this one, or maybe we could say if we increase the time, this is order 10 or something. Then one can see that this is more closer to the potential minimum. And as I mentioned, the slope changes suddenly. Therefore, this has much faster time scale to reach the minimum. So this faster goes to minimum. But here it just remains because it's still the potential is flat. So therefore, this place, the larger phrase, just goes to the minimum, and then we have gradient. This gradient will bring other places to go into the minimum. So we have the shock wave. So that is what is happening. So this is very similar to the first order phase transition, but we don't have the barrier. So what stops the field value outside bubble is just the time scale, because of the potential is so flat thanks to the condition of the inflation. Okay. Similar to the first order phase transition, the energy of the potential is eaten by the bubble wall. Then actually this can be found in the figure here. So one can see that so the down part is the evolution for the energy densities. One can see that when this kind of nonlinear uh, uh, dynamics happen, the kinetic energy, gradient energy suddenly increase, but potential energy is eaten by them. Then those gradient energy dominates the whole system, and then they collide with each other. Every energy becomes uh, the becomes the uh, particles and waves. Okay, this is what is happening soon after the low scale inflation. And this is kind of genetic. So it's as long as the inflation scale is low enough. So this is totally different from what we have learned in the textbook, because after inflation, it's not the oscillation. It's, like a phase transition. Okay. So once we have this kind of bubble or dynamics, once we are sure they will collide with each other, then we could say we can just do the similar thing for the first order phase transition. Order one of the energy, it becomes the gradient energy, and they collide. So we get gravitational wave. The frequency of the gravitational wave is typical distance between the bubbles. That is, Hubble inverse, because this mode is from the momentum mode of Hubble from the end of the inflation condition. Okay, therefore one can use those knowledge to write the spectrum of the gravitational wave, which is given like here. So one can see that I think this is uh, perhaps interesting, because one can see that those inflation over very large scale from MeV to EeV would be dropped in the future observation of the gravitational wave. This is not primordial gravitational, much higher frequency. Uh, uh, and sometimes, for instance, in the EeV case, perhaps this model is already constrained by the LIGO-Kagura data. So already we can we can exclude some possibility of the inflation. In addition, for the PTA case, we may already have some hint for the inflation if inflation scale is GB, then one can have a perhaps better fit for the PTA data. Uh, in particular, this is a kind of GEB scale inflation could be suggested from the trans-Planckian censorship conjecture. Okay, this is one thing that I want to uh, tell you. Another thing is that maybe it is also related to the baryogenesis. But this is a recent, a figure from a recent paper in collaboration with Miguel in Barcelona University. Uh, so so what we consider is that we assume some shock wave. So this does not need to be the inflation shock wave, but just a shock wave by some axion-like particle. And we assume this axion-like particle somehow coupled to the Higgs field in the standard model. Then this shock wave will induce a Higgs world. Then, I assume this axiom coupled to the Chern-Simons term. Then, this shock wave has, change of the field. Then we have because this is moving, then we have phi dot. Phi dot means we have the chemical potential. And because we have the Higgs wall, then, we have the spheron in front of the world because it's a symmetric phase. Then we can just get a baryogenesis. When the plasma goes through the two walls, then we get baryons. So the parameter region is something like this in the language of the axion-like particle. The interesting point is that this is consistent with the model called ALP inflation. This is a low-scale inflation model, and I think this is an interesting direction to study because we need to care a lot of other constraints, and because there is shock wave at this moment, the author didn't, at least me, I didn't notice that there is shock wave, so we need to reconsider several things like the how to reheat the universe, how to do several calculations. But anyway, this could be an interesting direction. Okay, this is the end of my talk. Basically, I have talked that the inflation scale may be low, but what is the genetic prediction? We show that if the inflation scale is super low, say if it is like lower than 10 to 5 GeV for inflection point inflation or genetic inflation, or we could say if the inflation for the hilltop one, it's 10 to 9 GB, or for some of the inflation genetic inflation with scale 10 to 12 GB, we must or we may have shock wave depending on the scale soon after inflation. So therefore, the dynamics, the picture of the reheating is slightly different. It's not from the coherent oscillation, but it's from the shock wave formation. Then we have studied that this shock wave may hit each other, may generate gravitational wave. And if this is just time as a fast order phase transition, then we can have a relatively strong gravitational wave that can be probably in the not too distant future. Also, I just forget to mention, in the hilltop inflation case, we genetically have the domain wall formation because we have a very nonlinear, dynamics or inhomogeneous evolution of the universe. So when the shock wave uh, expand, then it will sometime pull the field on the hilltop into the wrong vacuum. Then we form the domain world. So this domain world is not long-lived. So it's safe, but we may have some imprint. So we need to think more carefully what will happening. So at this moment, I don't know, but I just say that there is domain world formation. Also, we have mentioned that there is baryogenesis. There could be links to the baryogenesis, and this is kind of minimal, just coupled to the inflaton to the Higgs. That's it. So then we could have the baryogenesis. I should say this inflation scale should be close to the electroweak scale. So this is really low scale inflation. And also we have other possible discussions. For instance, we may consider the primordial black hole formation due to this kind of shock wave dynamics. And we need to be more careful about the reheating, as I mentioned, because once we have shock wave, this is anisotropic. This is not very the thermalization is not very usual, so we need to consider some denser place, some sparser place. So yeah, those things are, I think, definitely interesting. So if you are interested in them, so feel free to contact me. I'm very happy to discuss those things with you. And perhaps from those discussions, we can get more generic limit for the low scale inflation. Okay, that's it. Thank you very much.